In Prob 1, we did lot of problem with tossing a fair coin, rolling a fair die, or drawing a card at random from a well-shuffled deck, or picking a ball at random from a box. In these cases, all the outcomes were equally likely. Now, when we are working with density, then also we have an analogous concept which is called the uniform distribution. In order to understand this, think of a subset of R, say an interval, or a region in R2, or some region in R3. I will call this region in all these cases S. So here S is a subset of R, it is subset of R2, and this is subset of R3. And I will denote the size of the set, in this case length, in this case area, and in this case volume, by the common symbol this. Now I want to pick a point at random, uniformly from this set. So in this case it will be a point like this that I can denote by a real number x. In this case it will be a point here that I can denote using two real numbers xy, and in the third case, so I have got some random variables. Here x and y are both random, x, y, z are all random, and they are jointly distributed in the sense they are defined over the same sample space. They are outcome of the same random experiment. Now, when do I say that this has been done uniformly, that is, everything is equally likely? Since there are infinitely many points, uncountably infinitely many points, I just cannot say all the points have same probability. Then what I want to say is this. Take any subset of S. Say I take this interval, it need not be interval, some subset of S which I call A. Similarly, I can take some subset, some regions of S here. Similarly, I can take some sort of a ball or something, A. Then the probability that your point lies in A will be size of that divided by size of S. So in this case it will be length of A divided by length of S. It will be area of A divided by area of S, volume of A divided by volume of S. Now you may ask, well, if it is an interval, I know what is meant by length, but if it is something complicated, how do I compute length? That's a different question, and we shall take a closer look at that near the end of the course. But for now, we will be working with only those type of S and A for which length or area or volume can be easily computed. Suppose x is chosen uniformly from S 0 to 1, that is the unit interval in R. We have to find the CDF of x. First, let's draw a picture. So intuitively, you are picking up any point at random. What we have to find out is the CDF of x. That is, given any little x, what is the probability that x is less than or equal to x. Now, if I take little x here, little x, what is the chance that x will lie to its left? Obviously 0, because x must lie between 0 to 1. So I immediately have, if x is less than 0, then fx is equal to 0. Suppose I give you x here, then what is the probability that capital X will be to its left? Of course, surely, because x must lie between 0 to 1. So we have this case. So the only thing that remains to be discussed is x lies between 0 to 1. So let's see what happens then. The probability that x lies to the left of little x, this means x lies here. So this is our A. And what is the length of this? The length of this is x itself. And what is the length of S? The full thing, the length of that is 1. So it will be x divided by 1, which means it is just x. So that is our required CDF, which we can sketch like this. It is 0, then it moves up 45 degree, it reaches the point 1, 1, and continues as a horizontal line. Consider a disk of radius r centered at the origin. So this is the disk, not just the circle. I am considering the inside also. Now I pick a point at random uniformly from the disk and I measure this distance x. So that's a random variable, a non-negative random variable. Your job is to find out the CDF of x. I will just give you a quick hint. X cannot be negative. X cannot be more than r. So it must lie between 0 to r. So now you can figure that out.